Little is more important to an oil or natural gas drilling operation than the drilling fluid itself. A drilling fluid must exhibit a set of properties that often contradict each other in order to best perform its tasks within a well. Its purpose is to clean the bottom of the hole with cuttings, while also cleaning and lubricating the bit. On top of this, it must maintain the walls of the hole, transport cuttings to the surface, as well as prevent entry of formation liquids. Since a drilling fluid must perform so many different tasks, it requires a delicate balance of ingredients, a recipe. In order to understand the necessary properties of a drilling fluid, we must first examine the path it takes throughout its circulation. The drilling fluid, essentially a mud, begins its journey in the mud mixing hopper, in which all the necessary ingredients are added to our concoction. This edited mud flows from a suction pit through a suction line to the mud pump or pumps. These pumps provide the necessary power to drive the mud along the discharge line, up the standpipe, across the rotary hose, down the cowlee, drill pipe, drill collar, and finally the drill bit. It is here that the mud is used to blast away sand, rock, or whatever lies in the way of the drill bit, while simultaneously cooling and lubricating the bit. The fluid then carries the cuttings from the bit up through the annulus and out of the hole. Once the fluid and cuttings exit, they go through a series of refining processes, including a shale shaker, desander, desilter, mud cleaner, and centrifuge, before it can reach a settling pit and begin the process again. Before the mud is ready for circulation, it must have certain properties. These include plastic viscosity, yield point, gel strength, cake thickness, pH, resistivity, and density. The difficulty lies in the fact that adding one ingredient to the mixture may optimize one property, but cause the mud to diverge from a previously met property. This is such a problem because every hole is different and each well requires a different set of properties to best accommodate the oil or natural gas operation. The plastic viscosity and yield point are determined using a viscometer, a device which measures the viscosity of mud at varying RPMs, typically from 3 up to 600 RPM. The gel strength can also be found from the use of a viscometer by mixing the mud at a high RPM for a period and quickly decreasing the RPM to find an instantaneous maximum viscosity. A filtration test allows us to see how much liquid can pass through the walls of the formation, and the result after all the liquid is depleted is a filtration cake, of which has a thickness comparable to the thickness of mud coating the well's walls. A resistivity meter measures the resistivity of the drilling fluid, and a litmus test can measure the pH. A conventional mud balance is responsible for calculating the density by filling a known volume and using a precise balance to measure the mass. Density is very important to a drilling operation because it controls formation pressure and it also helps wellbore stability. The first step in designing your mud is to have a warm, soft water, that is, water both low in calcium and magnesium. Once the water is soft, bentonite can be added. Bentonite is an absorbent clay and the main ingredient in the mixture. Salt is added to increase shale inhibition properties and provide a suitable environment for the wellbore logging tools. The order is important because adding salt before bentonite will prevent the bentonite from hydrating. Next, lime, or calcium hydroxide, is added as an alkalinity source to neutralize unwanted acidity encountered during drilling, which appears in the form of hydrogen sulfide and carbon dioxide. CC16 thinner, or lignosulfates, are mixed into the flocculated clay to decrease the artificially high viscosity produced from the lime. The thinner restabilizes the flocculated clay colloidal system by bonding its negatively charged micelles, which are fatty acids with hydrophilic heads, to the outside of the bentonite particles, breaking the bonds of the calcium ions. Next, DrillPack adds polyanionic cellulose (PAC) polymers to the drilling fluid, which adhere large polymer molecules of PAC to the mud. This causes the filtration cake to become thinner, slicker, and less permeable, making the drilling fluid more efficient and reducing its filtration volume. Finally, barite, or barium sulfate, is mixed into the mud to control its density. This is important because the mud must resist the formation pressure of the surrounding rock and prevent collapse, while simultaneously limiting its hydrostatic pressure such that drilling fluid doesn't leak back into the rock. In order to maximize the efficiency of a drilling operation, engineers must apply these ingredients in the correct ratios and order for each specific well. In other words, Each rock formation provides a different set of challenges to face and a different recipe to design.